Yeah. Now we will be moving on to the inferential statistics world. Till now, we have computed the values, descriptive statistics. Then we also have arrived at some kind of mechanisms of finding the intervals. The moment we know the distribution or patterns in the data, most of our calculation goes with the normal distribution world itself. Y is what is covered in this chapter. Now, we are going towards the inferential. Now I have done some calculations. Now based on the calculation, I should be able to make some conclusion about a particular value. Like Infosys gives 15% return in a year. It's a statement, right? Congress secures 50% of the seats in this particular constituency. It's a statement. So I am making statements, generalizing the statements based on the data which I have collected. The data which I have collected I am calling as sample, and based on the sample doing some statistical calculations on the sample, and then I am saying I am generalizing the conclusion. That is what is the world of statistics. And statistics is not about computation, right? There's a very big misconception among the people. When they say come calculation, they call it as statistics, but that is not the scope of statistics. Based on that calculation, I have to generalize something, right? And I have to work on samples of data only, because if I'm calculating on whole data, there is nothing to generalize. That's already a generalized statement, right? If I am taking the heights of all people in the country, then it's an exact value. The average height is an exact value. It's not an approximated value. But if I take it only for 100 people, and based on that I make a generalized statement, that is what is statistics trying to do, right? Instead of going to 100 crores people and measuring their heights, probably if I measure the heights of some 1 lakh people and I can generalize it, that is where I am getting the advantage. That is what statistical tests or calculations are typically aiming at. So that is where sampling becomes a very important aspect, because I have to always work on the samples. So from that standpoint, so to make valid references or inferences about anything, to decide something, to infer something, my data should be random in nature. The sample which I am collecting should be random, because out of 1 lakh, or see, okay, I am ready to pick 1 lakh people to find out the average height. But if 1 lakh people are specifically chosen from short people, then my height is a biased height. Average which I am calculating is a biased one. Rather than that, if I pull from the entire group randomly, then probably my height may be same as the population's height itself. That is what the statistics talks of. Whatever the sample you are pulling, it should be a random sample. In that random sample, there are some names. Simple random sample versus stratified. Simple is, in this group, if I have to pull out 2 people, in a random fashion, probably I will pull out 2 people, right? Or from a group of 1000, I have to pull some 50. In some random fashion, probably I will write 1 to 1000 in a chits in a basket, and draw some 50 chits, and those 50 will be picked up. That is what is a simple random sample. It's a simple, it's randomly picked, that sample. Now, sometimes as a part of simple random sample, people also use the concept of systematic sample. It's nothing but out of that list itself, if I have to pick 20, I'll say every 20th pick I'll select. Instead of just picking up 50 as it is, I'll say no, I'll pick every 20th element. That's also in a random fashion itself. The 50 which I select is every 20th element. So that's also a form of random sampling itself, but it is in a systematic manner. Some procedure I am using to pick up my random sample. Whereas when I talk about stratified random sampling, if there are multiple kind of groups in the data, let's say females and males, or youngsters versus old people, there are different groups in the data based on some characteristics. Now I want the representation from all the groups. Probably that height calculation itself, if I take the 1000 people in my sample and 1000 of them are males only, it will be a biased height, because it's estimated that on an average female height is lesser compared to a male height on an average. So if I don't include the females in my list, obviously overall average is showing on the higher side. Correct? So in those cases, if I know some specific characteristics of the group, I first divide the data into groups. And from each group, I pull out the data in a random fashion. So if I have to select 1000 people as a part of my sample, and if I know 48% are females, 52% are males in the whole population. So even my sample, I'll make it in such a way that 48% of my sample will constitute females and 52% will constitute males. So I'll take the data of, so first I'll break my whole sample into two groups, male and female. 520 males, 480 females. That's how I want my 1000. So out of this 480, so out of females, gather any 480 females. Out of males, gather any 520 males. What happens in that situation is, there is an equal representation across all the classes also. Otherwise, there is a possibility that I would be picking up all the males, or 80% males, 20% females only, which could bias my calculations. So in some cases, especially where there are multiple characteristics in the data, right, multiple types of groups present in the data, it's better to follow a stratified random sampling approach rather than a simple random sampling. Let's say NSE has to, or BSE has to compute Sensex. Sensex is nothing but top 30 highly performing companies as far as their market capitalization is concerned. Now, if that top 30 are coming from one or two industries only, let's say banking and IT, or banking, IT and pharma, only 3 industries. Now, if the Sensex says we'll use only these 3, we will use the top 30 companies which will be coming from these 3 industries, and they say this is what is the reflection of the overall market. That is not the reflection of the overall market, right? It's a reflection of 3 industries. Probably there is no airline company in that 30. There is no cement companies in that 30. There are no real estate companies in that 30. Now, how can you say these 3 industries are representing the whole economy? Unless there is a decent representation from different kinds of industries in that calculation, I cannot say that it is a reflection of the overall market. Correct? So, that is what we call as stratified random sampling. Okay. Now, I will take 5 from banking, 4 from IT, 3 from something, because that is looked at in proportion to the total. Oh, there are so many pharma companies. The size of the pharma industry in India is this much, which constitutes 3% to the GDP or something. So 3% of my total stocks should be pharma stocks. Now what is that they are doing? They are stratifying the whole data, what they should contain, and within that they are pulling out some of the values. So if I pull the values on a random fashion, they don't do it randomly there, but if I pull out the values on a random fashion after I create the groups, that is what we are calling as stratified random sampling. Now, when we are doing sampling, there is always an error when I take the average of the sample versus the average of the entire data. There will always be some scope of error. That error we call as sampling error. If I take a sample mean versus minus the population mean, or sample standard deviation minus population standard deviation, whatever it is, that is what we call as a sample error. Now, this sample calculation which we are doing, let's assume average, right? Just I'll take it as a very simple data here. On a random basis, I want to take the heights of 3 people from this group. Randomly I pull out 3 of you. Some 3 will come out of this group, their heights. I'll get the average height. Now I'll repeat the experiment second time. Probably some other 3 people will come now. It need not be the same 3 people. Some other 3 people will come, which means their average height will be different. Again repeat. Another average will come out. Now what is happening? When I am repeating the experiment n number of times, of pulling out the same sample size from this group, the average that is getting calculated is differing in each of the cases. Right? In one case it may come out as 160, in some other case it may come out as 163, in some cases it may come out as 165. Depending on which 3 people or which few people are being pulled out. Right? So that distributes, which means that is also a random variable. The sample mean, sample average is also a random variable. Random variable means it can take different values. So sometimes it is becoming 163, sometimes it is becoming 165, sometimes it is becoming 162 or 0.5, any value. Right? If there is a big group and I have to pull 3, there could be any number of values that can be occurring. Right? So that is what we mean by it's a random variable. So any random variable will follow a distribution. Correct? Any random variable will follow a distribution. It could be a binomial, it could be, because this is a continuous distribution, it should be either a continuous uniform or normal or some kind of a continuous distribution, log normal or some form of a continuous distribution. So the sampling distribution is nothing but because the sample mean or any calculation we are doing on the sample, it can have different values every time you select the sample, because you are selecting the sample on a random basis, either simple or stratified. There is a randomness in that. Because you are selecting the sample on a random basis, there is always a scope for difference in the calculation for each sample of the same size of the same group. Right? So that distribution is we call as the sampling distribution. So sample mean, there could be different values to the sample mean based on the sample I am taking. There could be different values to the sample mean, and when I find out, when I try to plot the frequencies of those sample means on the y-axis and the values on the x-axis, that is what is the distribution. the probability on the y-axis and the sample on the various values on the x-axis. That is what I am calling as a sampling distribution. So sampling distribution, now depending on the shape it follows, will make the estimations accordingly. So that is one major aspect here. Sample, though we are considering, I am taking one sample of size n. The calculation which we are doing, that will differ every time the sample changes. So if I have to generalize it, okay, let's try to understand this concept. Out of this group, I have taken a sample of few people, measured the height. Some 165 came out. Some other, once more I did the process. It came out as 163. Once more I did. It came out as 167, because the contents of the sample will change, which means the average also will change. But if I have to, so in one case 163, one case 165, one case 167, probably some more times I do, some more values may come out. Now which one should I make as my range, or what is the conclusion I should give? When I defined in the beginning, from the sample calculation, we have to make a generalized statement. Each sample is giving different numbers. Right? One sample is giving 163, one is giving 165, one is giving 167. So what conclusion I make? That is where there is a statistical test that comes into picture, or interval that comes into picture. Okay, 163, 167. Now I'll say, based on the distribution of that sample, I'll say, okay, there is a 95% chance that it will lie between this and this. There is a 99% chance that it will lie between this and this. The moment I can establish the sample distribution is a normal distribution, right? The moment I am able to establish that the sampling distribution is a normal distribution, I can very well say what is the 95% limit, or 95% interval, or 99% interval. I am 95% sure that the population's average lies between 163 to 167. I will not say that it is 165. Sample, it is giving 163, 165, 167. But once I know the pattern of all those numbers, if I know that it is following a normal distribution pattern, my estimate will come out as, no one will ask for a point estimate, because we are nowhere gods. Right? No estimate can be a point estimate. The estimate always will be an interval estimate. But at what level of confidence? I will say I am 95% confident that the population average will be between 163 to 167. So if someone says, what is the chance that an Indian male height is 170 or above? We can very well find out using the normal distribution pattern. How many standard deviations away from the mean, convert it into a standard normal distribution, and finally based on the area in that curve, you will say this is the chance that an average Indian male's height is more than 170. Right? That's how the sample distribution will play a key role. Now in this, the data captures which we do, they are of two forms. One is a time series data and two a cross-sectional data. When we say time series, we collect the data over different time periods. Every year, every month, every monthly sales data of a company, monthly stock price of a company. So we are collecting the data over different time periods. Then we call it as time series. But if I collect the data at one time period only for various entities, 20 companies today's stock price. Today's stock price of 20 companies. That is what I call as cross-sectional data. I am not collecting the data over a period of time, but at a point in time, I am collecting the data for various entities. That is what, so sometimes we collect the data, let's say the today's car prices of 500 brands in the country. That is a cross-sectional data. The other thing I may say, the prices of the cars or the sales of the Maruti Wagon-R over the last 50 months. That's a time series data. One entity over different time periods we call as time series data. One time period for different entities we call as cross-sectional. And when these two are combined, we call it as a pooled kind of a data, which will have both time series as well as cross-sectional into it. Right? So especially when we talk about a longitudinal data, where we are talking of multiple characteristics over time of a single entity itself. Like for one company, probably I'll take the stock price, I'll take the profit, I'll take the sales, I'll take so many parameters of one company over the last 5 years, over the last 10 years. So we are talking about there is a time series part, there is a cross-sectional part also. Both are there, but one entity, multiple parameters of that entity over multiple periods. That is what we call as the longitudinal data. And when I say panel data, over time periods, multiple entities, one parameter, which is like stock price. 5 companies over the last 5 years. If I take one company over the last 5 years, it becomes time series data. 5 companies over the last 5 years, it becomes a panel data, which is like a cross section or a combination of both time series as well as cross section data, and we end up calculating any one of we end up collecting any of these forms of data, and depending on the kind of data we are collecting, whether it is time series or cross sectional, the actual tests and the calculations will differ. Of course, that is outside the scope of our CFA. That becomes more into statistics in depth. But the moment I collect time series data, I may have to apply some kind of formulas and calculations. The moment I am looking at cross-sectional data, and again, just for your comfort level, in level 2 we will cover to some extent. When I look at more of a cross-sectional data, we apply a concept called regression. When we look at time series data, we apply a concept called time series analysis, which are completely two different worlds, where there could be a little relation between the two, but they two go completely on different directions altogether. Both are targeting estimation. Both are targeting making conclusions. But depending on whether our data is time series or cross-sectional, we'll calculate appropriate things, and based on which our conclusions go in that direction. So for that we need to understand what forms of data could be there, again from an exam standpoint. This is the whole heart of the entire statistical calculations. Now we are saying sample mean it has a distribution 163, 165, 167. There is some distribution associated with that. What this theorem says is, if your sample size is very large, and according to statistics, very large means greater than 30. Instead of 3, as I used in the earlier example, if I collect 30 minimum, 30 people's height, out of 1000 people whom I have, randomly pick some 30 people, measure their average height, 30, 40, whatever, anything greater than 30. Randomly pick up 30 and measure their average height. Every time the average will differ. So, because of that we are saying the sample will have some kind of a distribution. Now what it says is, if the sample size is large, above 30, the sample distribution will follow a normal distribution. That is the understanding normal distribution becomes the key. You don't need to bother about what distribution it is. Automatically the sample distribution will follow a normal distribution with mean equal to the population mean and variance equal to population variance by n. That is what is the, if the sample size is 30, right? Now let's say we have calculated we have taken a sample of 30, right? We have taken a sample of 30 and the sample average has come out as 165. Now what it is saying is, now one sample I got 165, one 167, one has 163 and so on, right? Now if the sample size is greater than 30 in all the cases, which is, I am saying 30 people randomly I have chosen and found out their heights. Now what it says is, this is following a distribution, random variable, so different values are coming out. What it says is, this distribution follows a normal distribution with an average equal to the average of the sample mean, which is equivalent to the population mean, and whatever is the variance of this sample, variance divided by n will be the variance of the sample distribution. So this is the heart of all calculations. So you don't need to bother whether your original data is in normal form or binomial form or log normal form. You don't need to bother at all. The reason being, the sampling distribution will become a normal distribution if your sample size is greater than 30. If your sample size is greater than 30, the sampling distribution will directly become a normal distribution whose mean is equal to the population mean and the variance is equal to the population variance divided by the sample size. That is what is the central limit theorem saying, which is what we would be using for all the interval construction problems. It's not exactly equal to the population mean. The average is equal to the population average, but there is a standard deviation in that, which is equal to sigma by root n. The variance is equal to sigma squared by n. Standard deviation is the square root of that variance. So which will be equal to sigma by root n, which means there is an interval that we are building. We are not saying, see, with the samples I have collected this. Now if the average is 165, I will not say that the population average is 165. I am saying population average is 165 with a standard deviation of plus or minus 5. So probably I am saying my 95% limit, 95% confident that the population average lies between 160 to 170. I am not saying a dot there, right? What this theorem is saying is, if your sample size you are collecting is higher and higher, see, if it gets equal to population, Let's assume in a simple way. My population is 1000. My sample is 30. Now instead of 30, if my sample is 1000, which is equal to population, then the average, any time I compute, it will give the same value. No deviation in the value, because the population is 1000, sample is also 1000. I have to pick all 1000 people from that list. So there is no deviation in the value. So standard deviation will be 0 in that case. But because I am doing it with 30, what I am saying is, it may be equal to 165 with some deviation existing. So if the deviation is 2, let's say, if the deviation is 2, what we are saying is, the 95% confidence level is 165 plus or minus 1.96 times 2, because 2 standard when I say 95% limit, as per our normal distribution, 1.96 standard deviations from the mean. Standard deviation is 2 in our case. So I am saying 1.96 into 2, which is almost 4. 2 into 2, 4. So 4 to the left of the mean, 4 to the right of the mean. So I am saying my 95% confidence interval for the population average is 161 to 169. So what is that I am saying? I am 95% confident that the population average will lie between 161 to 169. So there is only 2%, 2.5% confidence that it will fall below 161, and only 2.5% confidence that it will fall above 169. So here the generalizing is not a bullet point generalizing, it's always a range based generalizing, right? So the central limit theorem is simply saying that it will approach the population mean, but there is a variance associated with that, which is equal to sigma squared by n. Now if n becomes larger, n is nothing but sample size. If the sample size 30, 40, 50, 100, 200, 500, this is going lesser because n is in the denominator. If n is higher, the standard deviation is going lesser. So 1.96 times standard deviation will go lesser, right? N is going higher means variance is going lesser. Standard deviation will go lesser because it's the square root of variance. Standard deviation lesser means 1.96 times standard deviation will go lesser, which means the interval is actually getting narrowed down. The accuracy of the estimate is becoming more and more. Interval is getting narrowed down. Accuracy of the estimate. Now I am 95% confident that it will lie between 163 to 167 instead of 161 to 169. Now when I increase my sample size, probably I may get to a conclusion saying 95% confident that it will lie between 163 to 167. Right? So that is where the larger the sample I am collecting, the accuracy of the estimate can be improved. And the reason why we are depending heavily on central limit theorem is, the moment I know that the distribution is normal, we can very well compute the probabilities. Any distribution, the moment I know the shape of the distribution, the computation of the probabilities will become much easier. And with normal distribution, we have been seeing for quite some time, how do I calculate the probabilities? Lesser than this, greater than this. So once I know that my sample distribution follows a normal distribution with a mean equal to the population mean and a variance equal to sigma squared by n, I can very well construct 95% intervals, 90% intervals and blah 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 stuff. That forms the basis for generalizing. Right? So this is the major concept, probably one single concept in the statistical world that is driving the entire estimation principle is the central limit theorem itself. Now, so that Now, we said that the variance of the sampling distribution is sigma squared by n, which means there is some kind of a deviation in the sample mean, right? So that is what is the technical term for that is standard error. The standard deviation of that sampling distribution, which is nothing but sigma by root n, that is what we call as the technical term for that is standard error. In case population, generally the term is sigma is for population standard deviation, S is for sample standard deviation. Both are standard deviations only. If sigma is used, it is like population. If S is used, it is like sample. But both of them are standard deviations only. So, if sigma is given, you use sigma by root n. Otherwise, if S is given, you use S by root n. So, as far as you are concerned from your exam standpoint, you don't need to bother whether you are using sigma or S, except for one or two cases which I will talk of. So, whenever the question is about standard error, all you are doing is sigma by root n. He will give all kinds of data in the question. He will give average, he will give so many other data which is redundant. When the question is about compute the standard error, all you are doing is sigma by root n, which is the standard deviation divided by the root of the sample size, right? And in most of the cases, population standard deviation is not known because we don't know what is the population, how many elements are there in the population. So that's where generally S is used, which is sample standard deviation. These two are nothing but standard deviations only. If you remember the first class when we computed the population standard deviation versus sample standard deviation, we divided by n for population standard deviation and n minus 1 for sample. So if he gives right from the raw data, that will be the situation. But generally what he says is he will directly give the value. Given the population standard deviation is 5, given the sample standard deviation is 4.5, he will not start from the raw data for you for calculating at least standard error. Right? Because, for calculating standard deviation, probably he may start from the raw data, but to calculate this, he will directly give whether it is a population standard deviation or a sample standard deviation. Whatever is given, you are simply doing sigma by root n. Now let's look at this and what else is there. As the sample size increases, as we have discussed, the standard error decreases because sigma by root n. N increases, denominator increases, sigma by root n decreases, gets closer to the population mean because the interval also decreases. Interval decreases, so your sample mean is coming more and more accurate with the population mean. Okay, one numerical we'll try out. Sample mean is 10. Population standard deviation is 5. Sample size is 25. What is the standard error? What is the standard error in this case? Sigma by root n. What is sigma? 5 by sample size, root 25. So 5 by 5, which is coming out to 1. Straightforward. So here the sample mean of 10 has no meaning in it for this question. As far as this question is concerned, I don't need to bother about the sample mean. Now, what should be the sample size if the standard error needs to be 0.5? So he is asking about 5 by root n. I don't know what is n. This should be equal to 0.5. Standard error should be 0.5. So 5 by root n should be 0.5. So root n is becoming 5 by 0.5, which is 10. So based on which I am getting n equal to 100. So if my sample size becomes 100, my population, standard error will be 0.5, which will be halved. Earlier it was 1, now it becomes 0.5. So the narrowness comes up. in the interval. Now, so as sample size approaches infinity, which is almost equal to population, then there will be no error at all. Because if I take the sample as big as population, then there is no deviation. So that's where if someone says if I am collecting the whole population and doing calculation, then I don't consider it as statistics, because there is no generalization. Generalization itself is a population calculation. Only when there is some kind of uncertainty associated, where some probability distributions and all can be assigned, then only we are getting into the world of statistics. Now look at the next numerical. What should be the sample size if the width of the interval needs to be 0.5? If the width of the 95% interval, if the width of the 95% confidence interval has to be 0.5, what should be the sample size? What is the interval? What is the 95% interval? Mean plus or minus 1.96 times the standard error here, because we said sample distribution will have a mean of a population and a variance equal to sigma squared by n. So whenever the question, okay, I'll give you a simplified way to remember this. When the question always talks about find the confidence interval of the sample mean, if the word is there, confidence interval of the mean, then you use it as 1.96 times standard error. When the question is about what is the 95% confidence interval of the original data itself, then you take 1.96 times standard deviation. Just remember in these two aspects. If the question is about the interval for the mean, take 1.96. The first value is still the same. Both of them population mean. So the mu part is still the same, but 1.96 times the standard error if the question is about the sample mean. If the question is about the data, then we'll take 1.96 times the standard deviation, because he may ask both the kind of questions, and for confusing you he may give both the answers also, right? So here if I want to find out the sample with respect to the sample mean, I want the width to be 0.5. So what is the width now? Mean plus or minus or plus 1.96 SC minus of mean minus 1.96 SC is the width, because it lies between mean minus 1.96 to mean plus 1.96. The width is the difference between the two, which is when I am simplifying it, this is becoming 2 into 1.96 times standard error. That is equal to 0.5. The width, when I am subtracting the maximum value minus the minimum value, mean plus 1.96 sigma minus mean minus 1.96 sigma. Mean is getting cancelled off, and that is becoming twice 1.96 sigma. So 3.92 times standard error is equal to 0.5. From here I can find out standard error is equal to 0.5 by 2 into 1.96, whatever the value that comes out. Sigma by root n is equal to this much. Sigma is already given as 5. All I need to find out is n. So what should be the sample size again? The same kind of a question. So the question can be slightly tweaked for different scenarios. At the end, you remember, if the question is on standard error, I can directly compute sigma by root n. Irrespective of any other values being given, I don't need to bother about the other values. Now, the next stage which we are getting into is, now I am estimating. We are creating estimations for the population mean. Right? Using a sample. Sample is giving some number. Based on that number and distribution of the sample, applying central limit theorem, we are now going forward to make the estimation about the population mean. Population mean, population variance, any of the calculations. So, if I am using something as an estimator, what should be its characteristics? Here what are we using? We are using sample mean to estimate the population mean. Correct? We are using sample standard deviation to estimate population standard deviation. We may use median to estimate sample mean also. So anything which we are using to estimate a population parameter, whether it is mean or standard deviation or whatever I want to estimate, the estimator which I am using should have some characteristics. One, it is unbiased. If I take the average of all the possible values of the estimator, it should be equal to the population value. It should be very close to the population value. That is what central limit theorem is also defining. See, sometimes people may say, probably why not use median? Why are you using sample mean? Why not median? Now what happens is, if I take the expected value of all the medians, it may or may not be equal to the population parameter. So that's where the median is getting eliminated from the list, and we are still sticking to the mean itself. Because when I am taking the mean, the average of all these, of all the various samples, the estimated expected value of the estimators should be equal to the population parameter itself. That is what we call as unbiasedness in the parameter. So what he can give in the exam is probably okay, the sample mean, or a person is using x to estimate y. He tried to compute the expected value of x, and it is becoming more or less same as expected value of y. So which characteristic of the estimator does it correspond to? Unbiasedness, efficiency, consistency. When the question is about expected value of the estimator equal to the population value, we call that characteristic as unbiasedness. Second, your estimator should be efficient also, which means compared to any other estimator which I have, this should have lesser and lesser sampling error. Sampling error is also resulting in standard error also. Compared to others, probably if I find out sample mean, sample median, sample mode, blah 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 stuff, compared to any other estimator, this should have the lowest sampling error. Sampling error is samples value minus the population value. This should have the lowest possible error. That is what is efficient, which is very close to the actuals. The samples estimator is very close to the population value. That is what is making it efficient. Then the third thing is about consistency. If the sample size is increasing, the standard error should go lesser and lesser and lesser. The estimator should go more closer to the accurate. These are the three problems. One is saying the average of the samples should be equal to the population value. That makes it unbiased. This should be better than any other estimators. That makes it efficient. If the size of the sample is increasing, the error should be decreased and become more closer to the population value. This is the consistency kind of a characteristic. So the typical thing from an exam standpoint here could be some characteristic of this kind would be framed in the question. And so he has collected the data initially of 25 values, but he thought he should collect for 100 samples, which has resulted in a standard error reducing from 20 to 5. So which characteristic of the estimator are we talking of here? Consistency. As the sample size increases, the standard error is coming lesser and lesser, which is more talking about the consistency parameter of the estimator. Right? So any estimator we are looking at, these are the three characteristics that it should satisfy. Now we are coming into the estimating part, where we are differentiating between a point estimate and an interval estimate. We have discussed something about it. Point is like a bullet. 165. That's a point estimate, which is very rare in the finance world or probably any world. Very rare that we make point estimates, which is like some direct formula. Mean 165. So the population mean is 165. It becomes very rarely correct. Right? If I ask you what is the return tomorrow, it's as good as saying 1%. Very, very rare that number will be met, because all possible values can be occurring. Unless you have fixed it, it's very rare that you will get that same exact 1%. It could be slightly more, slightly less. So that is where we are always defining an interval range. In the interval, as we have already defined, 95% interval, 99% interval I will build, where I am saying whatever is the point estimate I got, 165 plus or minus 1.96 times the standard deviation, if I want 95% confidence interval. So the standard error I am taking, standard deviation is nothing but standard error in case of sample mean. So 1.96 times the standard error. Now what is that 1.96? Where is that 1.96 coming from? One, it should be a normal distribution. For a normal distribution, the 95% limit is 1.96. Right? Because we are assuming as per central limit theorem, if the sample size is greater than 30, the sample distribution will follow a normal distribution. Right? So if the sample size is given more than 30, directly the interval estimate which I am making, I can make based on the normal distribution. If he is asking find a 95% confidence level estimate, we are directly using the sample mean plus or minus 1.96 times the standard error. So if we give standard deviation, we will do sigma by root n to find out standard error, and we are giving a 95% confidence interval around that. Sometimes the terminology he may use is, he may use the terms as 95% confidence interval, or he may call it as 5% level of significance. These two mean one and the same. Even if he is saying 5% level of significance or 95% confidence interval, both mean one and the same itself. So when he says 5% level of significance, what you are trying to find out is the range within which the actual value will lie given a probability of 95%. Because 1 minus 5%, which is 95%. So, a 95% confidence interval is what we are trying to build. Even if the question is saying 5% level of significance, because it's a very common value, common term to be used, the error term. 5% level of significance, if he says, it's nothing but build a 95% confidence interval around it. Right? So, that's where we are saying point estimate, which is nothing but sample mean, plus or minus standard error. Reliability factor is based on the distribution. So, if it is not a normal distribution, the 95% does not contain 1.96. Right? So, which means if the sample size is much lesser than, if in case in the question, if the sample size is less than 30, it need not be a normal unless he explicitly specifies that it is normal. It need not be normal, which means I cannot use plus or minus 1.96 there. Getting it? As long as the sample size is greater than 30, I'll directly assume it as normal and use it. But if it is less than 30, I cannot use a normal. That is where we are discussing of some other distribution also along with normal, which is called as T distribution, which will come slightly later. If the sample size is less than 30, we use another distribution called T distribution. If the sample size is more than 30, we'll use it as normal distribution. These two. Yeah, this is what we are talking of T. T is more or less same as normal. The only thing is, it is not as peaked as normal. Now, the better thing for you to understand is this graph itself. If the normal is having a peak of this much and a gradual fall, what happens in case of T is, it's slightly less peaked, fall is also more or less gradual, but what happens is in the tails, it is having more frequency compared to the normal. So, the simple way to describe T is, it is flatter compared to normal and it has fatter tails. The two major contexts that we define with respect to T is, it is flatter and it has fatter tails compared to the normal distribution. And what we are seeing is, as the sample size is increasing, it will merge with the normal distribution shape. If the sample size is 2 or sample size is 8, what you are seeing is the lower one, the inner one, is for a sample size of 2. The dotted one is for a sample size of 8. Now, as the sample size goes up to 30 and beyond, the graph of the T distribution will merge into the normal distribution. So, the T distribution graph should be exclusively dependent on the sample size. And that is what they call as a word called degrees of freedom. The T distribution is actually characterized by what is called as degrees of freedom. Right? Without getting into the technicalities of it, as far as our comparison of the means is concerned, the sample means kind of stuff is concerned, the T distribution, the degrees of freedom for it is always 1 less than the sample size. If the sample size is 10, degrees of freedom will be 9. Sample size 20, degrees of freedom will be 19. So, here when he is showing degrees of freedom is 8, it means sample size is 9. When he is saying degrees of freedom is 2, sample size is 3. Sample size, degrees of freedom is 1 less than the sample size, n minus 1. N is your sample size, n minus 1 will be the degrees of freedom. Now, what it says is, if the degree, and if he gives a table or some cutout of the tables he can give in the exam. Right? So when he is giving a cutout of the table, you have to look out for the value. For the t distribution, they will give degrees of freedom. The values corresponding to different degrees of freedom. Now if the sample size is 10, you have to look out for a value corresponding to 9 degrees of freedom. Right? And what you are seeing is, as the degrees of freedom is increasing, probably up to 29, because sample size is 30 means degrees of freedom is 29. As the degrees of freedom is going up to 29 or more, what you will find is the graphs of the t distribution and the normal distribution more or less merge. That is where what we are saying is, we can use normal distribution as an alias instead of a t distribution. Only for smaller sample sizes, to frame intervals, we will use t distribution. And what is the characteristic of the t distribution? The tails are fatter. If the tails are fatter, my interval will be wider. Interval will be wider. So probably if I am using plus or minus 1.96 in case of normal distribution, the same thing for a t distribution could be 2.05, 2.1, something like that. And now for t, we don't need to remember any value, because different values of t will exist for different sample sizes, because t is characterized by degrees of freedom. So for each sample size, a different value of t will come out. So because we cannot remember literally all values, we don't need to remember any standard value also. The only thing probably which you can do is, if at all he does not furnish the value, assume that it is normal. At least calculate the interval based on normal. Slightly increase the interval and choose your option. If the interval is given, if you say 95% interval, probably plus or minus 1.96. Slightly take, slightly towards the left, towards the right. You will have only one option choice which will meet that criteria. Right? The other two will be probably lesser in size, the interval wise. So in this case, what he will do is, he will put a slightly wider interval. So instead of saying that I will not choose, I don't have the t value, so I cannot compute. Here he is trying to test just wider, slightly more wider compared to a normal distribution. That's a kind of interpretation he is expecting from you. Now that is where this we have already looked at. Sample mean plus or minus whatever is the value, the z value, which is 1.96 or 1.65 or 2.58, depending on the 95% levels and 99% levels and 68% levels. That much times the standard error. That is what is our total calculation all about. And of course, if the sample, if the size is very less, we are resorting to a t distribution. Now, this is all under the assumption that the sample distribution follows a normal distribution. But if he explicitly gives, it does not follow a normal distribution, because only when the sample size is above 30, right, this approximately follows a normal distribution as per central limit theorem. But if the sample size is less than 30, there is no need that it will follow a normal distribution. Either he has to give explicitly that it is following a normal distribution. If he does not give, if he gives explicitly that it is not following that it is following a normal distribution, then you can use either a z or a t. But if it is not following, if he explicitly says it does not follow a normal distribution, and even the sample size is also less than 30, because if the sample size is more than 30, Whether it follows or not, you are approximating it to normal. But if the sample size is less than 30 and explicitly he says it does not follow normal distribution, then there is no estimate that you could do. Right? So the best way to categorize that, I think I have tabulated it somewhere. Yeah. This is the way you have to look at the tabulation aspect. If you know that the data is normal for a small sum and the variance of the population. Okay, I'll give a small flow chart for you. Normal. If I am saying, I'll ask a question, is the data normal or not? So the answer could very well be yes or no. If the data is normal versus if the data is not normal. The next question that comes is size. Size greater than 30. Here also size greater than 30. Here the option again will be yes or no. Here also the option will be yes or no. Then one more question that we ask is the population variance known? Sigma known. Versus here also I'll ask, is the sigma known? Now in each of these cases, what we are saying is, when the sample size is, or first of all, when it is normal, not normal, which is this path, in this path, if the sample size is very, very small, which is in this path, if the sample size is very, very small, I cannot use either T or Z. If the sample size is large, as we have said already, I can use a normal distribution because it follows a normal. Right? Even if the data is non-normal, but if the sample size is more than 30, the sample distribution will still follow a normal distribution. So that's where I can use either Z. Here also I can use Z, because as long as the sample size is above 30, I can directly use Z. If the sample size is below 30, simple, I am giving a simple logic for you. And even this complex flow chart, you forget about it. Sample size greater than 30, you go with Z, which are your values, which are known. 1.96, 2.58, those are the values. If the sample size is less than 30, two options. One is the population variance known or not known. Right? Or is it normal or not normal? Normal means some data, some distribution can be applied. Not normal means nothing can be applied. Right? So under these two conditions, one is a small sample size and explicitly given that it is a not normal distribution, we cannot use either Z or T. Greater than 30, directly we can use Z. We'll take some numericals which will give us that comfort level. Just look at this. Sample size 49, sample mean 90, population standard deviation is 14. 95% and 99% confidence interval. So should I use Z or T here? Z, because here he doesn't need to give me whether the data is following a normal distribution or not, because sample size is greater than 30, so I can directly take it to be normal. So I am using Z distribution, right? So my standard error is how much? Sigma by root n. 14 by root 49 is 7. 14 by 7 is 2. That is my standard error. 95% confidence interval is what? Mean plus or minus 1.96 times standard error. So 90 plus or minus almost 4. You do the actual value. 1.96 times 2. I am rounding off to 2 into 2. So 90 plus or minus 4. So I am saying 86 to 94. That is the 95% interval. Right? When I say 99%, I will use plus or minus 2.58 times the standard error. Almost 5. 2.5 times 2 is plus or minus 5. So I will say 90 plus or minus 5. So the 99% confidence interval is 85 to 95. So I am 99% sure. Probably the plain man's way of interpreting it is, I am 99% confident that the population average will lie between 85 to 95. Right? Only 1% chance that it will fall beyond this limits. Now what about the second one? In the second one, he has to explicitly tell you whether it is normal or not normal. If he says it is normal, you have to find out, he has to give you the t value corresponding to 24 degrees of freedom. Because the sample size is 25, one lesser. So corresponding to 24 degrees of freedom, he has to give you the t value, right, for 95% as well as 99%. Only when those values are given, then only you can compute. If he does not give it as normal, obviously you can write your answer cannot be computed, cannot be estimated, because sample size is lesser, and even if he explicitly gives in the question that it is non-normal, your answer should go for cannot be computed. But if it is given it as normal, then you apply a t value. He has to give the t value, and as I said, if he does not give the t value, you compute it based on z, but put the interval slightly more than that. Now if I compute it using z, assuming that he has given it as normal, now what is happening? My standard error, sigma by root n, 14 by 5, 2.8, right? So my 95% interval will become mean plus or minus 1.96 times 2.8. Let's assume rounding off 2 times 2.8. So 5.6. 90 plus or minus 5.6. So I am saying 84.4 to 95.6. This is as per my Z. Now because this is not Z, this requires T, make it slightly wider. If the option choice contains slightly wider on both sides, making it probably 83.5 to 96.5 something, then choose that as your answer, because T will be slightly wider compared to the Z, because this is almost 25, right? If the sample size is 1 or 2 or 3, then T will be more wider compared to Z. But what we are seeing is, as the sample size is increasing, T is more approximately coming closer to Z. So there will be a slight modification itself. So you can estimate your values like that. In case he does not give, Or sometimes what he gives in the question itself is he will put a table. He will give it as degrees of freedom and 2.5% area. 2.5% is in one tail. 2.5% is in one tail, which is 95% confidence interval. If he gives 0.5%, then it is corresponding to 99%. 0.5% in one tail. So 1% overall. Because this is also symmetric. T is also symmetric. 1% overall, which is 99% confidence interval. So what he will do is degrees of freedom, he gives some numbers like this. And he gives the factors, the values. 1.94, 2.31, 2.22, whatever. Some values he will be giving. So corresponding to your degrees of freedom 24, you have to pull out this value and do it as plus or minus that number. Instead of 1.96, you will apply that number. Right? Like if I have to, this Excel part you don't need to look at. But in tools like Excel, I can actually give, let's say, 5%, which is 2.5% I have to give. If I want 95% confidence level, I am giving 2% for 24 degrees of freedom. 2.5% corresponding to 24 degrees of freedom, it is 2.39. So, instead of doing plus or minus 1.96, I have to do plus or minus 2.39 times the standard error. Of course, either he has to give you this value or you will slightly widen the answer. Only two option choices. Now, till now we have been talking about the larger the sample size, the better it is. Because it will become more and more consistent. The consistency principle of the estimator will be satisfied. It reduces your standard error, increases the accuracy of the estimate. All good things are there. But it can result in more costly exercise. Because if I have to collect the data from more and more samples, sometimes it's not as easy to collect the data of many. If I have to generate questionnaire, let's assume I want to talk about who wins this election. Right? There are some 10 lakhs people in this constituency. But I am thinking just by collecting 1000 people's opinions, I want to make it generalized. Now, as we are saying, the higher the sample size, the better it is. Now, instead of 1000 people, if I go to 10,000 people, probably the accuracy will go up. Now, to go to 10,000 people, I need more manpower. I need probably more resources in other forms. Resources have to be required. So, it's a cost versus benefit weightage. Just by taking 1000, if I am able to create this kind of an interval, probably by 10,000, slightly narrowed. That slight narrowing, just for slightly narrowing the interval, if I incur huge costs, then probably if it takes more time, if I have to take the interviews of 10,000 people, it may take more time compared to taking the interview of 1000 people. So my output will take 10 more days to come out, even by the time election results will come out. Forget about my opinion poll. So it's a kind of weightage between cost versus the benefit. So choosing the sample appropriately also. Sometimes if it is very cheap to gather more and more data, I'll gather more and more data. But in some cases, data collection is a very costly exercise. In those cases, I may not go with a large sample size. I may have to restrict myself to very small sample sizes, but still I may have to conclude the data. And just because I want to go for large sample, if they are coming from different distributions, which means I collect 1000 people from this, just because I want 10,000 people, I am collecting 1000 people from here 1,000 people of some other constituency, I bring in and club it into this just to generate 5,000. Instead of pulling out all the voters from this place, I club the 1,000 which has been collected from somewhere else just to make it 2,000 or 5,000. Then that's of no use. So if the large sample actually is coming from different distributions, then there is no use with that data. And the most biggest disadvantage is cost. It will definitely increase my cost as I have to collect more and more data. So these are some of the negative aspects that are associated with my sample collection process. And in my sample collection, I would be subjected to a lot of biases. This is a very typical thing which we come across. Now, first thing, sample selection bias. What did we define? Sample has to be random in nature. Now, intentionally, if I omit some data because it is not available, right? Some data not available, so I have omitted it. Then it is nowhere random. I have to collect it. But if I am omitting it, then it means it's nowhere a random sample for me. But most of the times what people do is if a particular data is not available, they will omit and take the remaining data. That itself is making it biased. That is what we call as a sample selection bias. Because of that, our estimate may go wrong also. 1. 2. We talk about survivorship bias. What is that survivorship bias is? If I am looking at multiple periods, in some cases, I want to calculate some averages and all. Especially this happens with mutual funds, hedge funds and all these kind of funds. What typically happens is, some funds might have got closed out. Either because they did not perform well or some other new product came as a killer product or whatever, that fund gets closed off. Now, when I am trying to compute the average of different years, I will not, the elements which are there last year will not be the same as the elements which are there this year. Because some of them which have really poorly performed, I did not include in the calculation. They got closed down. They got closed down and they did not get reported. So I did not use them for the calculation purpose. Some kind of adjustment has to be made, right? See, last time I had 1 to 10. Now the item number 1 has poorly performed this year and I did not include the item number 1, but I have included item number 11, which has performed well. Now what is happening? If I look at this group versus this group, the average might have fallen. But because the composition is different between the two groups which I am computing, probably it may show that the average has gone up. Right? That is where we are exposed to a survivorship bias. In case, and in this again applies heavily to unregulated industries or unregulated markets. Hedge funds is a very unregulated kind of a market. The fund performance has to be reported by the fund managers. See, because no SEBI, no interventions will happen for a hedge fund. Now because of that, let's say you are all different managers of different hedge funds. Right? I am the person who is computing some average performance of the hedge funds. Hedge funds are giving 20% return overall. I am a person who is doing that kind of a computation. Now, what is the basis of my calculation? The data which is supplied by you. Because you are your own bosses there. Based on the data which you are supplying to me, I am doing a computation using some formula. If you don't supply the data to me, I don't even know that you are running something like that. Now what happens? Last year you have supplied, but this year you did not supply. The general tendency is when you don't perform, you don't supply the values. So what happens there is, the calculations which are coming out will be overestimated, because only the good will be taken, the bad will not be computed. So there could be a result of overestimation. So the survivorship bias simply says some of the things which are removed either because of poor performance or expiry or whatever, they may pull away my average and my conclusion may get biased. So I have to make sure that if I am comparing over different periods, I have to make sure that the survivorship bias does not come into picture. 2. Then the next bias which we are typically exposed to is the look ahead bias, which is I am computing some value today as of today's value, but I don't have today's data. I have taken the last month's data to compute today's value. Like if I say, the best example I generally use in this case is computing the P by E ratio of a company. Very common thing in the finance industry, in the investment industry. The P, which is the price, is available on a daily basis. Market price keeps changing every day. But E, which is the earnings, which is the profit of the company, is published only once in a quarter from the quarterly report which the company publishes. Now let's say they have published the last quarterly report on December 31st. Today I want to compute the P by E of the company. P is as of today, E is as of 31st December. Now whatever the number I am getting may be a biased number, because both are not belonging to the same time period. That is where I am talking of a look ahead bias. I am assuming that that same relationship will continue overall. If the P has gone up, probably E also will go up, which may or may not be the case, because that I will come to know only after 3 months when they really publish their next E. Right? That is where we are exposed to a look ahead bias in terms of the sample analysis. Then we are even talking about data mining bias, which means the moment I establish some pattern in the data, I focus only on different statistical calculations on the data without looking at the economic meaning to that. Right? Just because the data is giving this relationship, probably I have done some calculation, correlation, something on the data, and the data has given me this relationship. The best example I use in this case is, I take my company's sales for the last few years, my revenues out of the trainings of the last few years. I take the GDP of Uganda, nowhere related. But statistically, I try to find the correlation between them. It may come out as 0.8 or 0.9. Let's say if both are growing, what is the correlation? How both the variables are moving together. Right? Probably my sales are growing in the last 5 years. Uganda's GDP is also growing in the last 5 years. When I try to put the relationship between the two, it may come out as 0.8 or 0.9. Now immediately my statement comes out that my revenues are very heavily dependent on Uganda's GDP. Or the other way also, Uganda's GDP is heavily dependent on my revenue. No economical meaning to that. No relevance to that statement. So what happens is the kind of samples which people collect also, once it has been established, there is a strong relation between my sales and Uganda's GDP. Every year I prefer collecting Uganda's GDP value. The way I collect the sample, I prefer collecting Uganda's GDP every year, because at one point there was some kind of an establishment, there is a relationship between my sales and Uganda's GDP. Right? That is where, which means we focus only on data and churning of the data without looking at the economic significance of that. The way we collect the data, right? Sometimes some people say small companies give more returns compared to large companies. Right? Even the job world people talk about small companies pay heavy salaries compared to large companies. Right? Now, is it in the realistic sense? Or is it because some people have observed some data in the past and they have found that the average small companies' salaries are more than the large companies' salaries? It could be in either of the cases. Right? Previously, probably someone has done some statistical data and he has found some relationship and all. And finally, he is saying every year the small companies have to pay 10% more than large companies, which may or may not make any economic meaning sometimes. Right? If it is relevant across all the periods, then probably I can generalize it. Otherwise, what happens is, because of heavy focus on the data and the output which data has given, sometimes we tend to ignore the economic significance of that, the real world significance of that. Does it really exist or not? The Uganda's example which I was talking of. So that is what we are subjected to, data mining bias. And the final one is the time period bias. Just because the data is available for last 20 years, I collect the last 20 years data and do some calculations. Now what happens? That data could be too long a period, where the relationships could have changed over time. Now probably earlier there must be relationship between the stock market and gold market. But now there may not be a relationship. Just using an example. There may not be a relationship or may not be a strong relationship, because along with gold there are so many other investment avenues today. Right? So if I take that 20-year data for last 20 years and do the analysis, probably I may not get any conclusion out of it. So what time period data I have to take depends on the problem which I am analyzing. Too long a data or too short a data also, time period wise, only 1 year I take. Now what happens? This 1 year probably could be a boom year. So everything is rising. Some relationship could be there between stock and gold. I did not consider any fall year. Right? But if I consider 20-year period, on the other hand, probably the relationships would have changed over this period. So understanding the cycle, business cycle, collecting the data specific to the business cycle also plays an important role. So that is what we call as time period bias. How long a time period data we are analyzing? Is it too short or too long? Because both of them are problematic. That is what. So what happens is, when we are collecting the data, one side we say we have to collect random, and two we are saying a reflection to the actuals. But in our process of collecting the data, we go through these kind of biases. Either I omit some of the elements because they are not available, or probably I am ignoring some of the values which were there earlier when I am using for comparison purposes, survivorship bias. The formulas which I am using for computing the values are different time periods. The price of this period versus earnings of some other period, which is a look ahead bias. Or I am depending excessively on the data output that I have got, that I am forgetting the economic significance of that, where I am exposed to a data mining bias. Or I am collecting the data over a very long or very short period, where I am getting exposed to a time period bias. So we have to make sure that these kind of biases don't crop in our data selection kind of a strategy, right? So this is the very basic introduction into the sampling part, where the focus is on again confidence interval construction and some of the aspects of standard error and central limit theorem. Once these basic fundas are fine, you should be able to solve the question from this chapter.